Hello everyone. In the previous session, you have already studied about the connectivity relation and it is represented by R infinity, right? I have clearly explained this concept with an example. Please go through that video. Now, in this session, let me prove the theorem of that. In the sense, a connectivity relation R infinity can be expressed as union of all the relation. So this is obvious. Why? Because I have given a counter example for this in the previous session itself. Suppose if A is any set with cardinality n, if there exists a relation, something like that is what we have going to define, right? Suppose if I have a set A with some elements, I am going to define a relation with the Cartesian products, right? Whatever may be the elements inside the relation. So if A is any set with a cardinality n and R is a relation, R infinity is an infinite relation. What we say it is connectivity relation can be expressed as union of all those relations. Anyhow, it is true for a counter example, that is we have already proved it for a digraph. Now we have to put the same statement in wording format. So let me do that. Suppose let me take any two elements, say A, B in a given set A. I have chosen A and B as two elements in an assumed set A. Fine. Clearly, there will be n number of, when I say vertices, when I say points in a set, it represents a vertices. Fine. So if I have an elements A and B in a set, definitely there will be infinite number of points in between these 2 points. In the sense, suppose if I have a point A here, I have a point B here, there may exist n number of ways in order to reach this point. Suppose if I have a point say x1 here, x2 here, x3 here, then I can reach from vertex A to vertex B in n number of ways. Right? This is one of the way. Or else I can start with A, I can go through x2, I can reach x3, I can reach B. Right? So, given a vertex A and B, I can reach from vertex A to vertex B in any of the way, so that the path should be, path from A to B should be very small. So there is n number of ways to reach from a vertex A to vertex B. So let me take the vertices in between A and B are x1, x2, x3 and so on. Fine. Now what I'm going to do is I'm going to divide this longest path into sections. Like let me say a path from A to xi. Xi is one of the vertex in between. Fine. Again xi plus 1. Next vertex, like A to xi I have. Next vertex will be xi plus 1, right? So xi plus 1 to xj I have. Again xj plus 1 to b. In the sense, a given path is divided into 3 paths, subpaths. So that when xi is equal to xj, meaning is, let me start with A, I have to reach B, in between I have n number of points. Suppose I have a point xi here. When I am going to reach from A to xi, if xi is equal to xj, meaning is that both the points are same. In the sense, the vertex is repeating here, so that it forms a cycle. Clear? But anyhow, we should not form any cycle. If there is a possibility to form cycle, as I already done the same concept while doing Dirac's theorem, we have to emit or eliminate this vertex. We have to remove this vertex. So keep on removing all those vertices. We have to repeat the same procedure. In the sense, when we keep on removing the vertices which forms a cycle, we will get a shortest path from A to B. Hope so it is clear. If you are finding difficulty with this, go through the theorem. Every UV work contains UV path. I have done the same concept there also. So if any vertex is forming a cycle with the other vertex, we have to remove that particular vertex in order to avoid the cycle, so that we will obtain a shortest path from a vertex A to vertex B. So if you keep on removing, we will get a shortest path. So if A is not equal to B, there will be no cycle, I can say. That is what I have said here. Suppose if any two vertex is same, that will form a cycle. But our intention is not to form a cycle. So if A is not equal to B, in order to avoid cycle, A should not be equal to B. Then the given path will be having no cycle. So I have already explained this concept in the chapter trees, right? If it has no cycle, then it will become tree, and there will be n minus 1 number of edges, right? I have proved this theorem. In a tree, there is n minus 1 number of edges. Since there is no cycle, so I can say this path will become a tree. There will be n minus 1 edges. Suppose that if A is equal to B, there will be exactly n number of edges. Or I can say a path is of length n. If it is not equal, then I can say a path is of length n minus 1 I can say. So A is not equal to B means I am not going to get any cycle. If A is equal to B, then there will be n number of edges, then the path is of length n. So combining all those paths, we can obtain n, a path of length n. Meaning is that I can form a whole relation by combining all the relation. Fine, a concept is quite abstract, but the thing is, when do we say a graph is connected? When do we say graph is tree? When it has no cycle. If it has no cycle, then there will be n minus 1 edges. But what I assumed is a set contains n number of vertices, right? So it should contain, if it has to contain n vertex, then A should be equal to B. This happens only when connectivity relation is expressed as union of the remaining all relation that is existing in the given path. So whatever I have explained, I have given the same in terms of theorem. You just go through the notes. Again, if you are finding confusion with that, I am ready to explain. Now, this is what the theorem is. Next theorem is, so the statement goes like this. If, let me take any set A and R is any relation on the set A, then we have to prove first one, R is reflexive if and only if In is less than or equal to M. Remember, here we have a term if and only if, so we have to prove both the parts. Converse part also we have to prove. Now, first let me assume R is reflexive, then let me prove In is less than or equal to M. In the next case, let me take In less than or equal to M, then arrive at R is reflexive. Let me prove this. What is the given thing is, in a set A, there will be n number of elements. Fine. So let me assume, let R be reflexive. So I have to prove In is less than or equal to M. So as I already told you, a matrix of relation R is reflexive. Just before going to prove the theorem, I am recalling the concept. So is reflexive only when do we say matrix is reflexive? Only when the diagonal elements are equal to 1, right? So this is what I have explained in the concept of digraphs. So given matrix is said to be reflexive only when the diagonal elements are equal to 1. So I have assumed as R is reflexive. Fine. So I can write in a matrix M, let me take elements as Mij. So if it is reflexive, then in a matrix of relation, element will be 1 when I is equal to j. Right? Why? Because look at the matrix representation A11, A12, A13, A21, A22, A23, A31, A32, A33. This is how we are going to represent the matrix. Now you can look at the principal diagonal elements A11, A22, A33. So we can say given matrix is reflexive only when we have 1 in this particular position. In the sense the value of I should be equal to j, Aij. So when I said Aij as elements of matrix, both the values should be same for principal diagonal elements. So that is how I have written 1 when I is equal to j. And it is no need to check for the remaining element. Either it may be 0 or it may not be equal to 0. Fine. This is how the matrix of relation is defined. Now, In is none other than, you'll come to study this concept again in fluid dynamics, which is there in 3rd semester. So, In is none other than unit matrix. We can represent this as delta Ij. We say this as Kronecker delta symbol. So, delta Ij, it says that In is nothing but identity matrix. Identity matrix, so let me write one example. See here, this is an identity matrix of order 3. So in this case, we can see that only diagonal elements are equal to 1. So I can write 1 if I is equal to j, 0 otherwise. But here it is not the case. It may be 0 or it may be equal to 1. Only thing is, only principal diagonal element should be equal to 1. Then only we can say given matrix is reflexive. Whereas in unit matrix, all the diagonal elements should be equal to 1. So I'll give you counter example. Suppose if the matrix of a relation is something like this. In this case, you can clearly note that all the principal diagonal elements will be equal to 1. So it is reflexive. But anyhow, we have one more extra element here. Fine. But in case of matrix, unit matrix In, we have only once in principal diagonal element. If you have one more element 1, say something like this, in any of these positions, it will not become in, right? So clearly from these two examples itself, we can notice that in is always less than m. Why? Because we have one extra relation in matrix of relation m, but we don't have the same in matrix of relation in. So clearly I can write from these two definitions, in is always less than or equal to m. I'm repeating the statement once again. As per the matrix of relation, it takes the value 1 when I is equal to j. If it is reflexive, I have already assumed that given matrix or is reflexive. So, principal diagonal element should be equal to 1 when I is equal to j. And rest of the things either may be equal to 0 or it may be equal to 1 when I not equal to j. Fine. Whereas in in, it is unit matrix, it should be equal to 1 along principal diagonal element. Moreover, all the rest of the elements should be equal to 0. Whatever may be the value of I or whatever may be the value of j, it will be equal to 0 only. Then only we can say matrix in. It is what we say unit matrix, right? Or identity matrix we can say. Now I have given a counter example. Look at these two examples. Where in matrix M we have ones in principal diagonal elements. Obviously it is reflexive, and we have one more additional element, say 1 in matrix M. But if you are going to add any additional element to in, it will not satisfy the unit matrix condition. So I cannot add any extra element to matrix in. So in is always less than or equal to m. Now let me prove the converse part. What I have assumed in first part is I have assumed R as reflexive. What I have arrived is in is less than or equal to m. Now for the converse, let me assume in is less than or equal to m. Fine. Now I have to prove that R is reflexive. R is reflexive. Fine. When do we say as per the definition of reflexive? Suppose if I have an element A, then A should be belongs to R. As per the definition of reflexivity, this condition has to be satisfied. Right? Now, what I have assumed is in is less than or equal to m. Now, definition of mij. In the sense, if matrix M has an element, say mij, it will take value 1 when I is equal to j. Am I correct? In the sense, the meaning of this statement is that if you are going to take any element, this matrix, any element say ai, aj in this particular matrix mij. I am repeating once again, this is capital M represent matrix and mij represents elements of matrix, something like aij. Now ai and aj are elements of this particular matrix. So from the definition of matrix, mij is 1 only when I is equal to j. Right? That is principal diagonal element will be equal to 1. So meaning of this statement is ai, aj should be belongs to R whenever I is equal to j. So if principal diagonal elements are equal to 1, why? Because in is less than or equal to m. In the sense, M matrix should contains at least the elements which are already there in in. So in in, all the principal diagonal elements are equal to 1. So clearly I can say ai belongs to R. So this is what the condition of reflexivity is. Therefore I can say R is reflexive. R is reflexive. Hope it is clear. Now for the same statement, second theorem is that we have to prove R is transitive if and only if m square is less than or equal to m. R is transitive if and only if m square is less than or equal to m. If and only if condition is again mentioned. Now we have to prove both the parts. Now first let me assume R is transitive. R is transitive. Now we have to prove that m square is less than or equal to m. Fine. Now I have two matrices here, m square and m. Now I have to assume the elements of matrix. So let me assume matrix of m as say mij and matrix of small m or m square. I have assumed matrix of elements of matrix m as mij and m square as pij. Fine. This is what the elements of matrix is. Now I am going to use suffix notation. In the sense, elements of pij can be written as sum of all. Let me take one suffix, k is equal to 1 to n mik into mkj. Shall we write like this? Why? Because, so in the suffix notation, I'll just tell you the suffix notation. How does it works? Mik, mkj, when you have elements something like this, here you can note that these suffixes are called as free suffix. This concept will again repeating in fluid mechanics. There you are going to study in detail. Anyhow, you just remember this concept. So when these two suffixes are repeated, then we can remove this, and in turn we can write this as mij. Clear? I am repeating once again. If this suffix is repeating, we can eliminate the repeating suffix, and thereby we can write these two terms as mij. What I have done is, I have written Pij in terms of matrix M. Why? Because M square is obtained by M, multiplying M. So that is why I can write Pij as Mik dot Mkj. Fine. Now we have to prove that M square is less than or equal to M. Now suppose that, let me take two elements, say AR AS in a relation and AS AT in a relation. That is what the definition of transitivity is, right? Suppose if I have an element, say AB, then BC should be there. Then only we can talk about transitivity. Then AC should be exist in the given relation. Then it is transitive, right? So repeating element should be there. Then this condition exists. Then we can say transitive. So I have assumed two elements with repeated values. I have to prove that AR, AT belongs to R. Then we can say it is transitive. Fine. Now, when I have taken AR, AS belongs to R, by using matrix representation, I can write this as MRS. Since it belongs to 1, so I can write it is equal to 1. If it does not belong, I can write it as 0. Again, from matrix, I can write MST is equal to 1. Since both the elements are equal to 1, let me take product of these two. I can write MRS into MST is equal to 1. Fine. Now, again by using the suffix notation, why? Because I have taken the elements of Pij as the product of Mik and Mkj. So again, since I have the repeated elements here, MRS into MST, product of Mik into Mkj is Pij. So I can write this as PRT. See here, I have removed this repeated suffixes. I have written only the unrepeated suffix. Moreover, product of M will be the elements of P. That is M square. Product of M is none other than M square. M square will be elements of the form Pij. So that is what I have written PRT. Moreover, since this product is equal to 1, this product should be equal to 1. It cannot be equal to 0. Meaning is that, when, remember, so when I have I'll give you simple hint. Suppose if I can write like AI, AJ belongs to R, clearly I can write matrix of relation Mij is equal to 1. And vice versa. Suppose if I have Mk or Mxy is equal to 1, I can write Ax, Ay will be in relation R, where Ax and Ay are elements of M. Similarly, I have PRT is equal to 1. I can write AR, AT belongs to R. Now, look at these two statements. What I have assumed is AR, AS belongs to R and AS, AT belongs to R. This is something like AB, BC. What I have proved is AC, that is AR, AT belongs to R. Therefore, I can clearly say R is transitive. Now, I have to prove the converse part. In the sense, let me take R as transitive. Fine. Now, we have to prove M square is less than or equal to M. Converse part I am going to prove. Now, suppose R is transitive. For any element Pij, I am using the same concept here. I can express it as product of Miks and Mij. Let me take the same expression. Mik into Mkj, where k is running from 1 to n. Clear? Now, suppose that, let me take Pij as 1. If it is equal to 1, then I can replace here, so that I will get 1 is equal to summation k is equal to 1 to n Mik dot Mkj. Fine. Since what I have assumed is R is transitive. Fine. Now, if R is transitive, suppose that an element AR, AS belongs to R as per the transitive definition, and AS, AT belongs to R, that implies AR, AT should belongs to R. This is what the definition of transitivity is. AS, AT belongs to R. Repeated elements, if it belongs to R, then AR, AT belongs to R. Why? Because R is transitive. That is what we have assumed is. Clear? Now, if this is the case, I can say matrix of, let me take matrix elements as Mij. Fine. So, Mij is elements of matrix M, whereas Pij is elements of matrix M square. See here at the beginning itself I have clearly mentioned Mij is matrix of M and Pij is matrix of M square. Clear? Now Pij is, I can clearly write, is less than or equal to Mij. Right? Pij is less than or equal to Mij. Why? Because suppose let me take Pij is equal to 1. If you are going to take Pij as 1, since we have already assumed as Mij is an element of M. So if Pij is equal to 1 implies Mij should be equal to 1. Right? Why? Because Pij is none other than product of M square. M square elements is Mij. So 1 is connected to other. So if Pij is 1, then I can clearly write Mij is also equal to 1. Clearly, if Pij is equal to 0, then Mij should be equal to 0. So from these two conditions, I can conclude that M square is less than or equal to M. So no need to prove this also. This is more than enough to show that M square is less than or equal to M. Why? Because as you note that if Mij take 1, Pij also take 1. If Mij is 0, then Pij also takes 0. It cannot go behind the elements of Pij. So clearly M square is less than or equal to M. I am repeating this once again. I have assumed R as transitive. I have to prove M square is less than or equal to M. Since I have assumed R is transitive, just I have written the definition of transitivity. That is AR, AS and AS, AT belongs to R. Then AR, AT should be in R. Now I have already chosen Pij as product of Mik and Mkj. I have written once again. Now Pij is an element of M square. So if it is equal to 1, as per the definition of M square, it is Pij. M square is none other than product of M's. In the sense Mij. So Mij should be equal to 1. If Pij is 0, then Mij should be equal to 0. So it cannot go behind that. So strictly M square is less than or equal to M. Hope it is clear. Now the next theorem is third one based on the same. Third one is that M is, or else I can say R is antisymmetric if and only if M intersection M transpose is less than or equal to In. So far what we have proved is first condition is for transitivity. Reflexivity. So R is reflexive if In is less than or equal to M. First condition we have already proved. Second one is R is transitive if and only if M square is less than or equal to M. You have to remember this condition as we are using this in the next theorems. So R is transitive if and only if M square is less than or equal to M. Clearly third one is, next one is R is antisymmetric if and only if M intersection M transpose is less than or equal to In. Now we have again if and only if condition. We have to prove both. Now let me take R is antisymmetric. Fine. I have to prove that M intersection M transpose is less than or equal to In. Now as per the definition of antisymmetric, if two elements say Ai, Aj in R and Aj, Ai in R, implies that both should be equal, right? As per the definition what it say, if AB, BA belongs to R, then A should be equal to B. This is what the definition of transitivity is. Now I have chosen two pair of ordered pairs in a relation. Since if AI, Aj belongs to R, I can write by using matrix definition Mij is equal to 1. If it belongs, if doesn't belongs, I can write it as 0. Again I can write Mj, I is equal to 1. Right? This implies that we can clearly note that if Mij, suppose if I have an element say Aij, transpose of that will be Aj. Clear? Now I have an element Mij here and it is a transpose. Clearly it is a transpose, right? So I can write M intersection M transpose. This is M intersection. Intersection is none other than common of both the matrices. Either it may be equal to 0 or it may be equal to 1. I can clearly write either it may be equal to 0 or it may be equal to 1. If the element belongs to relation R, I can write 1. If element does not belong to relation R, I can write 0. So I can clearly write M intersection M transpose is less than or equal to identity matrix. Why? Because we are going to get zeros and ones in identity matrix. Either it may be equal to identity matrix or it may be less than identity matrix, since we are talking about antisymmetry. Clear? Now what I have told is In is an identity matrix. It takes 1 when I is equal to 0, I is equal to j, and 0 when I not equal to j. This is what we have told, right? That is what we have to prove. We have already proved this. I am repeating once again. Since I have assumed A as antisymmetric, so I have chosen two ordered pairs in a relation. So as per the matrix of relation, I can write Mij is equal to 1 since it belongs, and Mji is equal to 1 since it belongs to R. Now, as per the definition of In, it takes the value 1 when I is equal to j and 0 when I not equal to j. Fine, when you are going to take intersection of, since Mi, if Aij is a matrix element, then Aj will be the elements of its transpose. If A is elements Aij, then A transpose will be having an elements like Aj. Fine, so that is why I have written the intersection of these two, in the sense common elements will be either equal to 1 or it may be equal to 0. If it is equal to 0, then it doesn't belong to R. If it is equal to 1, then it clearly belongs to R. Fine. Clearly, if you are going to take intersection, it should be less than or equal to In. Meaning is In matrix is 0, 1, 0, 0, 0, 1. Either it may be equal to, all the principal diagonal element may be equal to 1, or it may equal to 0 also. It may less than. Less than meaning is one of the element may be equal to 0. Clear? So I have proved one part. Next part, let me assume M intersection M transpose is less than or equal to In. Fine. What we have to prove is R is antisymmetric. Antisymmetric. Now, since In or delta ij one and the same, In can be written as delta ij. Delta ij is also equal to 1 when I is equal to j and 0 when I not equal to j. This is what the definition of In is. Now, both the Mij and Mji, in the sense both the matrix M and its transpose, cannot be equal to 1. Cannot be equal to 1. Why? Because if in a matrix, I'll give you simple example. Suppose if I have an element 1, 2 in matrix of relation, I cannot have same in transpose, in the sense I'll give you one simple example. See here. If I have a matrix, in a matrix 1, 2 relation is there. In its transpose, there will be 2, 1. Transpose in the sense R inverse, right? We are going to inverse it. So 2, 1 is there. Since 1, 2 belongs to R, it going to take value 1. But 1, 2 is not in its transpose, it going to take 0. Right? So clearly both the values cannot be equal to 1. That is, I can say Ai is not equal to Aj. Clear? Ai should not be equal to Aj. Then we cannot have Ai, Aj belongs to R and Aj, Ai belongs to R. This is what the meaning is. I have written it in a general form. Ai, Aj belongs to R and Aj, Ai belongs to R. So if that element does not belongs, we cannot say it is, we cannot talk about its equality. That is, Ai is equal to Aj. Then also we can say R is antisymmetric. See, one of the special property of antisymmetric is, if this pair exists, then we can talk about Ai is equal to Aj. If this pair does not exist, then directly we can say it is antisymmetric. See here, 1, 2 belongs to R, but 2, 1 is not existing in the same relation R. So we cannot further talk about Ai is equal to Aj. So as per the property of antisymmetric, we can say R is antisymmetric. So hope it is clear. Go through all these 3 theorems. If you are finding any confusion or any doubt, you can free to ask me. Thank you. Continue the next session.